Okay, this section is basically video notes for section 7.4. And we're going to talk about evaluating logs, but the first thing I'm going to talk about are what are logs. So this was written for class, but obviously I couldn't upload it in time. But the question is, what's the relationship between these numbers? So if you take a look at the first one here, right, I'm asking you guys, there's a relationship between these three numbers because we're trying to figure out exactly what a log is. So if you actually take a look at the three numbers here on the log, and you try to find a relationship with them, I can actually rewrite this with an exponential function. So this equation, so this can be looking like 2 to the 5th equals 32, right? If I take a look at the one that looks like this, I can actually write it as 5 to the 0 equals to 1. And if I have the next problem down somewhere, it may look something like this, and I could rewrite it like this, and these all hold true. So if you guys notice, these all logs can actually be written as an exponential function. In fact, if I take a good look at these guys here, this one is in the exponent, the 0 is in the exponent, and the 5 is in the exponent. Which takes us to this. A logarithm is an exponent. So if you actually take a look at the examples we just did, logs are actually equal to an exponent. So if we take a look at the general structure of it, we can say that log base b here is base b of y is equal to an x. And again, a log is equal to an exponent. So if I rewrite it as an exponential function, then it would look something like b to the x equals to y. So we can use this particular conversion of logs to exponential to logs to actually solve problems that may require some more work other than just trying to simply solve by using the properties of equality. Okay, so for example, if I have something like a log base 2 of 8 equals to x, and my job is to figure out what does it actually equals to. Again, keeping in mind that logs is actually equal to an exponent, we can go ahead and write it in this fashion. The 2 can become the large 2 base for the exponential equation. The x, again, is equal to the exponent, so that goes with the 2. And then, of course, the only number left over is 8, so that's what it's going to equal to. So we'll put it right there. So that makes it a lot easier for us to actually figure out problems that may look like this. So again, if you have a hard time seeing that this answer here is a 4, okay, we can rewrite this log form into an exponential form. So again, the little base 3 becomes a large base. The 81 is what it's equal to. And since log is equal to an exponent, that goes with the 3. And again, for a problem like these, this is very similar to the technique we learned last chapter. We want to change it so that these two bases here are the same so we can start comparing them. Okay, so we can write 81 as 3 to the 4th. Okay, and again, what we're looking for is actually this x value, right, the exponent. So if I take a look in comparison, see the base here are the same, which means that the exponent should also be the same because they're supposed to be equal to each other. So the answer for this one is 4. And we can actually verify that because log base 3 of 8, 81 is equal to 4 because 3 to the 4th is the same thing as 81. So looking on the practice sheet, if I take a look at part A, that's the one we just did. So you can do the same thing with these other problems in that fashion. So here are the answers to those problems. After you try them, I'd suggest that you guys actually check them. So here are some helpful logs that you guys can actually use. So the first one is, if you have a log base b of 1, it always will equal to 0. And the reason is because if you change it to an exponential equation, it actually becomes b to the 0 equals to 1. So you can see no matter what base you have for a log base of b, it'll always equal to 0 if you're taking the log of 1. Okay. Another helpful one is log base b of b. That is always equal to 1. Okay, because again, if you rewrite it as an exponential equation, b to the first is equal to b. So anytime the base here and the log of the number you have is the same, it'll always equal to 1. So flipping the paper over, you'll notice that there are some of the things where you have the log of the number looking like a fraction. So the problems that are on this side from a through I, okay, again, it's really hard to see, like for example, the first one's -1, okay? But if we go ahead and use the conversion of exponential equations, that might be a little bit more helpful, okay? So if we go ahead and take the log of 1/7, okay, well, let's say that's equal to a because I'm trying to figure out what that is. Then I can see that the little 7 there becomes the base of 7. Logs are equal to exponents, so we'll write an a with the 7, and then we'll make it equal to 1/7. So going back to your exponential conversions, you know that if I can change 1/7 into the base of 7, if I actually write the exponent of -1. And again, you can see a matches with the spot of -1, okay, because that's what we're looking for is the a. So we can say that a is -1, okay? And the same thing can be done for all the other ones. So for your convenience, after you practice, you can check your answers with this one, okay? Now, looking at the other side here, a through d, you notice that now the base is a fraction. Again, we still can use the same technique here and change it into an exponent to get more of an idea of what it could be. So if I go ahead and take a look at the first one here, I can go ahead and let's see here, I'm missing the word log. Let's see if I can stick that in there. Okay, so we have that. And again, the little base, 1/5, becomes the large base now. The exponent is what the log is equal to, so we'll put an a in the corner, and that equals to 125. Now you should recognize that this 1/5 and 125, we can actually convert it with the base of 5. So for 1/5, we can write it as 5 to the -1. But because there's an a there, let's multiply -1 to a. And then 125 can be written as 5 to the 3rd. So again, we're only looking to solve the exponent here. So -a is equal to 3, but we're looking for a. So a is -3. Okay. So again, converting it to exponential form sometimes is a little easier to solve these problems. Okay, and for your reference, those are the answers. E through I is a little different. Again, notice that the base is larger than the number of the log. So what we can do here, again, same thing. Let's go ahead and convert this into an exponential form. So little base 36 becomes a large base. Log is equal to the exponent a, so we'll put that with 36, and that makes it equal to 6. Now, 36, we can write that as 6 squared, okay? And then remember, the 6 on this side actually has an exponent of 1. So looking at just, oops, sorry about that. So looking at just the exponent here, let's see here, let's go back here. Looking at the exponent here, 2a is equal to 1, okay? So we could write it as 2a equals to 1, divide by 2, which tells you that a is 1/2. Now remember, in terms of 1/2 in the exponent, we know that that means the square root. So if we go ahead and check that, you can see that 36 to the 1/2, or square root of 36, is actually going to be 6, okay? And for your convenience, those are the rest of the answers on the worksheet. So the homework you'll be doing tonight is to actually convert from exponential to logarithmic form. So taking a look at a on this left-hand side here, if I want to convert to exponential form, I would write it as little base becomes big base, the exponent 4, and that equals to 81. On the other side, I'm going to ask you to also go backwards. So again, this is an exponential form, so I'm going to write it as log base 8, big base becomes little base, of we know that the 2 is the exponent, so that equals to 2. And then 64 is the number I didn't use, so that goes in the spot of the log. And again, you want to practice it and see if you can get these answers here. So one last thing is to understand that that there are special logs, okay? If you ever see a log with no number in the base here, like this one right here, okay, that means that automatically it has a log of base 10. It's a very commonly used log, and so that's why if you look on the calculator, it actually have its own special key. So if you look on a scientific or graphing, you'll see the key that says log. That represents basically log with base 10. It cannot be used with any other base but 10. Okay, so this is the only thing that you can use it for. The other one that's really common is called the natural logarithm. The natural logarithm has a base e other than 10. Okay, and again, because it's not very productive writing this all out over and over again, just like the log base 10 of x, it's kind of like saying putting a 1 in front of x. 1x is the same thing as x. Okay, so if it has a base e, then they actually took a little bit of a shortcut and represent it as ln x. So again, if you take a look at your calculator, you should see a button that says ln, and you'll notice that you'll see that above it says e to the x. But in any case, ln means the log of base e. And remember, e is just a number, right? An actual number that we calculated out for continuous compounding problems. Okay, and it's really like 2.718 and so forth and so forth. Okay, so there's one more thing that might be a little bit complicated, so we'll do these two examples. One of the things that they want you to do is simplify. So if you ever see a problem that kind of look like these, you'll find out that you can rewrite them as a log function or an exponential function, but you have to recognize what form it's in. So taking a look at this example right here, let's say they want us to simplify this. I have no clue, so I'm going to go ahead and take a note here exactly what they gave me. So they gave me this 30, a log of 30, base 30 of 4, and since I don't know what it is, I'm just going to write down equal to a. Okay. If you see, this is actually giving you this problem is written in an exponential form. Again, this way I can't figure out what this whole thing is equal to, so I might as well try and change it into a log form. Okay, so if I do that, this will become log. The base here is 30, so that becomes a little base of this guy. We know that the exponent here is what it's going to equal to, so I'm going to write it as log base 30 of 4. Okay, so it's going to be written just like that. And we know this a here should go in this spot right here, so that's going to be a. Now, if you take a look, right, all I'm doing is figuring out what a is. Looking at this, the left and the right look exactly identical. It says log base 30, so that means a must equal to 4. Okay. Now, taking a look at the other problem here, right, this one happens to be in log form. Again, they're asking me to simplify this, which I have no clue, so let's say it's equal to a again. Looking at the way it's structured, okay, we have the base 2, you have the exponent a, and then you have this log of the number, which is the whole thing, 32 to the x. So if I go ahead and recognize that this is in log form, I'm going to go ahead and change it into exponential form. So this becomes 2 to the a equals to 32 to the x. These problems are very similar to the ones we did in the previous chapter. So if I change 32 with a base of 2, which is 2 to the 5th, okay, and again, all I'm looking for is the value of a. Since the bases are the same, I just have to compare the exponents now. So in this case, a is equal to 5x. It is possible to have an answer that's just not a numerical value, right? It can have variables in it. So this would be the answer to this problem. Anyways, try to do the homework, and then we'll go over this tomorrow.